Hello everyone, I'm Ying Jie from Institute of Information Engineering, Chinese Academy of Sciences. My presentation is a covert botnet in the cryptocurrency network. As we know, botnets are always one of the most effective attack platforms. A botnet refers to a group of compromised computers that are remotely controlled by a botmaster via CNC channels. Based on botnets, multiple types of Internet attacks can be launched, such as DDoS, email spam, Bitcoin mining, and so on. Traditional botnets usually use main CNC protocol like IRC, HTTP, P2P, and so on. The first generation botnets generally have used a centralized topology, but they usually suffer from a single point of failure problem. In response, attackers have introduced decentralized architectures based on P2P protocols, which are more difficult to take down. However, decentralized botnets are vulnerable to index poisoning and CBL attack. These issues have motivated botmasters to continually explore more promising ways to acquire new CNC channels. A new method that has recently emerged applies cryptocurrency and blockchain technology to build a botnet CNC channel. In cryptocurrency-based botnets, commands or CNC server address are embedded into a transaction by the botmaster, and bots extract this information from the blockchain via a hard-coded identity label. To better understand the COMBOT, some background knowledge of cryptocurrency needs to be known, including blockchain technology, transaction, operation, double spending. Since there is not much time, here we will not explain them in detail. Nevertheless, for an ideal botnet, current cryptocurrency-based botnets still have some drawbacks. The first drawback is heavy P2P traffic. To join the botnet, bots must include a corresponding cryptocurrency wallet application, so a large amount of P2P network traffic will be generated when synchronizing block data and enumerating the transactions. Second, commands will be permanently stored in the blockchain along with the transaction, so botnet activity can be traced on the blockchain. Third, the botmaster's sensitive information is hard-coded. So, to overcome the above drawbacks, we present COMBOT, a generic botnet CNC channel model in the cryptocurrency network. By utilizing URL sorting service and block explorer service, the bots can extract commands via a dynamic addressing scheme, and CNC communication is hidden in legitimate HTTP or HTTPS traffic. To avoid commands being permanently recorded in the blockchain, we present a cleaning scheme that is inspired by the double spending problem. We deploy a COMBOT prototype in multiple cryptocurrency networks and analyze its feasibility, cost overhead, resilience, stealthiness, and anti-traceability features. We also discuss possible strategies for mitigating the proposed botnet. This is the COMBOT architecture. The communication between the boat master and the boats includes 4 steps. The first step, the boat master embeds the signed and encoded command into the operator of a transaction and submits it to the corresponding cryptocurrency network. The second step, the boat master uses the RESTful API of a Block Explorer service to generate a URL with transaction hash. This URL can directly locate the transaction that contains the boatmaster command. The third step, the boatmaster chooses a URL shortening service and converts the URL obtained in step 2 to the custom URL that can be predicated by a URL generation algorithm. The last step, the boats share the same algorithm as the boatmaster and periodically send a request to the URLs generated by the algorithm. Once successful, the bots will actuate and verify the comment from the response. The above steps can be summarized into 2 actions: commands issued by the boatmaster and command actuation by the bots. Next, we will explain these 2 actions in detail. Income bot. The boatmaster inserts the command in the operator output script function of a transaction. A cryptocurrency network using the Bitcoin protocol is allowed to insert arbitrary data through operator. The limit size of the inserted data is 83 bytes for most cryptocurrency networks. This bandwidth is sufficient to embed commands. Longer commands can be further encoded or fragmented to fit with these limits. Commands are encrypted and signed with symmetric key and an asymmetric key, and then encoded in basic 16.4. To actuate the commands, CoinBot uses a dynamic addressing scheme based on Block Explorer service and URL shortening services. Both first run a URL generation algorithm based on URL shortening services to generate a set of URLs and randomly selects one of them to visit. The URL shortening service redirects our requests to the Blockchain Explorer service. Blockchain Explorer service responds the requests and returns the transaction information. The URL shortening service can replace long URL with shorter ones, and subsequently redirect our request for the shortened URL to the originally long URL. Some service permits users to customize a short URL, as these pictures. The boatmaster can replace the URL address of a transaction with a custom address. To predicate the URL address of the transaction, boats and the boatmaster must share the same URL generation algorithm. This algorithm is similar to DGA. However, the algorithm does not generate domain names but URLs. The URL address of a transaction can be generated by the Block Explorer service. A Block Explorer is a web service to search the blocks of a blockchain. It allows users to explore the entire blockchain of the platform they are using, including transaction data, block data. Most Block Explorers support multiple cryptocurrencies, and private RESTful API for querying and propagating transactions. We show several popular Block Explorer services in this table. Based on the transaction hash and the Block Explorer RESTful API, the master can form a URL to directly locate this transaction and look up detailed information. To avoid commands being written into the blockchain, we present a cleaning scheme. The cleaning scheme is based on two facts. The first one, if there are two conflicting transactions that have not been confirmed in the cryptocurrency network, once one of them is confirmed by miners, the other transaction will be considered invalid and will never be written into the blockchain. Second, each transaction has a fee attached that is given to the miner for their hard work. To earn more coins, miners will convert transactions with the highest fees first. The higher the fees a user is willing to pay, the faster his or her transaction will be processed. So, if the bots can execute the command before the transaction is made, and the bot master can withdraw this transaction by creating a conflicting transaction before the previous transaction, the command will not be recorded in the blockchain. To achieve this goal, the transaction containing the command should set very low fees to encourage a long confirmation time so that the bots have enough time to obtain the command. As shown in this picture, we refer to Bitcoin as an example. The bot master first embeds the command into a transaction and sends it to the Bitcoin network. This transaction A must be set with very low fee to ensure that the transaction confirmation time is as long as possible. Then both extract the command from transaction A, estimating the R bots have received the command. The bot master sends a conflicting transaction B that uses the same UTXO but higher fees. In theory, miners will confirm transaction B first. When transaction B is confirmed, transaction A will be dropped from the local memory pool and never be recorded in blockchain. In this scheme, there are two important problems should be considered. The first one is how low the transaction A fee should be set, and the second one is how long its confirmation time can be delayed. This determines whether this cleaning scheme is feasible. We verified the scheme in our experiments. We deploy a Coinbot prototype in multiple cryptocurrency networks. On the botmaster side, we use BitcoinJS lib, Litecoin lib, and Dash lib to create raw transactions and submit them to the network via BlockCipher. Our bots are developed based on Python 3.6 and run on 20 volunteer machines in multiple locations. The bots periodically access the URLs that are generated by the URL generation algorithm, and the URLs will change every day according to our algorithm. At first, they evaluate the parameters of the cleaning scheme, that is, to find the best confirmation time and fee. We developed a set of experiments with different fees, from 0 side bets to 5 side bets for 10 days on Lightcom and Dash. Our results are shown in these two pictures. When the fee is more than one side bet, the transaction can be confirmed in a short time. When the fee is less than one side bet, the transaction will stay unconfirmed for a long time. The shortest time is 16 hours. So, according to experiments, as long as the boatmaster sets the fee at less than one side bet, boats will have at least 6 hours to abandon the command. Next, we evaluate the feasibility of Combot. We create a command, download a file, mm.exe. The valid period is from 20 May to 20 June. The command size is 176 bytes. So we split it into 3 segments and add the command ID and the segment ID in each command segment. Then send this command to Litecoin, Dash, and Bitcoin testnet with different fees. The access frequency for URLs is set to once per minute. This finger plots the cumulative probability distribution of the time bots obtained the command. Our bots could get the complete command within 6 minutes. After our bots received the command, we sent 3 conflicting transactions that have no extra data with the same UTXO and 2 CBET fees to networks. This transaction were confirmed after 10 minutes, 7 minutes, and 6 minutes, but caused a double spending warming as shown in this picture. However, this warming does not affect our operation. We reset the access frequency to 10 minutes, 20 minutes, and 30 minutes, and the results show that when the access frequency is 10 minutes and 20 minutes, our bots received the command within an access period. When the access frequency is 30 minutes, about 19% of bots received the command within an access period. Therefore, if the access frequency is more than 10 minutes, we suggest that 2 access periods for the bots to obtain commands is appropriate. In conclusion, Combot is feasible and applicable to multiple blockchains. We analyze the performance of Combot. First, Combot is low cost. The cost of developing Combot depends on the value of the cryptocurrency itself. A better method for lower cost may involve using a testnet. It won't cost any money. Second, the CNC channel of Combot supports multiple blockchains and public services, thus providing it with high resilience. Third, compared to other cryptocurrency-based botnets, Combot have no cryptocurrency client. It is more difficult for detection systems to detect abnormal situations in large amounts of HTTPS traffic than in P2P traffic. Fourth, Combot introduces some web services, but there is no registration process in these public services, thus preventing the identity of the boatmaster from being exposed. Our cleaning skin keeps commands from being recorded in the blockchain. It reduced the risk of botnet activity being exposed. To mitigate the threat of these botnets, we discuss possible countermeasures. First, we recommend detecting the URL generation algorithm features of Combot from network traffic. Second, Block Explorer service providers should take more responsibility for detecting such a botnet. Finally, from the perspective of establishing a healthy blockchain ecological environment, we also recommend that researchers propose a more secure solution to prevent blockchain from being abused. Okay, that's all. Thank you very much.